Did you know that you are actually a wave? Seems weird, you're a collection of particles. But you are also a wave. That is the strange reality of existence that you will discover as you study Stage 2 physics. Sure, there's a lot of maths in physics. Actually, that's one of the reasons why I really enjoy physics. I also enjoy maths. But it's not all maths. There is a lot of it that is theory. Hi, my name is Edward. I'm studying a Bachelor of Science at university, specialising in maths and physics. After that, I'll be studying a Masters of Teaching. I also have a passing interest in trains, and that's cool because a lot of train analogies are used in Year 12 physics. Let's have a look at one of them now. During a science lesson back in primary school, my teacher took the class out to the oval. He stood on one side of the oval and he kicked the fence. We, at the other side of the oval, saw him do that, and then we heard the sound. The speed of sound is quite slow. The speed of light is faster, much faster, but it is still slower than infinity. If you stand in the middle of a train carriage with a torch in both hands, one pointing towards the front of the carriage, the other towards the back, and you turn those on at the same time, it will take a minuscule but measurable amount of time for the light to get from your torch to the front and to the back. And obviously that amount of time is the same because it's travelling the same distance. However, now let's say this train carriage is going very fast, maybe 90% of the speed of light. Well, the same thing happens when you turn the torches on. The light takes the same time to get to the front and the back of the train carriage. But what about somebody who is standing outside that train and seeing you go past? Well, to this person, they see the beam of light you shine towards the back of the train hits that wall a long time before the light from the torch pointing to the front of the carriage hits that wall. How can that be? For the person inside the carriage, the torches were turned on at the same time, the light travelled the same distance, front and back, and hit the walls at the same time. To the person outside the carriage, the torches were turned on at the same time, the light from them hit the walls at different times. Which one of these two people is correct? What actually happened? Did the light hit the walls at the same time or at different times? The reality of it is both of these people are correct. As you'll be learning this year, space and time change based on your frame of reference. It is correct to say the light hit the carriage walls at the same time. It is correct to say the light hit the carriage walls at different times. Let us move on from relativity and have a look at the right-hand rules. There are two right-hand rules, the right-hand palm rule and the right-hand curl rule. Both of these are related to current flow and magnetic fields. The right-hand curl rule. The current flow is in the direction of your thumb. The field is in the direction that your hand wraps around. So, if a wire has a current flow going this way, the field is going in this direction. The right-hand palm rule. Yet again, positive current flow in the direction of our thumb. Yet again, magnetic field in the direction of your fingers, but this time we keep them straight out, and you have a force coming out of your palm, as though you were just pushing someone away. Now, using either of these two rules can be quite complicated. Let's have a look at this example. We're told that the proton, which has a positive charge, is moving to the left, and that the magnetic field is directed upwards. If we were to align our hand on this screen, you'd effectively just be high-fiving the screen, telling us that the force is going into the screen, and that is what you would write as your answer. into the screen, or as is more likely, into the page, because this will probably be a piece of paper. Now, what about this example? Well, in this case, these dots tell us that the magnetic field is coming out of the screen, so we have to direct our hand in such a way that our wrist is touching the screen and our hand is sticking out at right angles. That's not going to be comfortable. And we haven't even looked at what direction our thumb is supposed to be going in yet. Part of the problem that students face with this is that they don't want to look silly in a test, and twisting your arm around like this can make you look silly. But you'll be getting the last laugh when you score full marks on that exam. Also, and I know this might sound silly, a lot of students get this wrong because they use their left hand for the right hand palm rule. Because many of them are holding their pen in their right hand, and so they just move their left hand about to find the correct way to position it on the paper. One of my friends during Year 12 kept making this same mistake. It got to the point where during tests and exams he held his hands out in front of him, found the L, not that hand, the right hand. This might seem silly, but he did very, very well in his marks. Have a look at the few examples on this page. Can you work out the strange ways in which you're supposed to twist your arm to try and make these examples work? Once you've struggled with that for a bit, try drawing that same diagram on a piece of paper and then moving the paper around, bending that. It'll be much easier than trying to twist your arm. So yes, sometimes during the exam, there are students that are doing this because that's how they can get this to work. And that's the most important thing. I started this video by informing you that you are in fact a wave. Let's examine this further. You might have heard of wave-particle duality. The fact that light is simultaneously a wave and a particle. The history of this is very strange and confusing. It got to the point where they were pretty sure that light was a wave. During one of his papers, Max Planck accidentally stumbled across light as a particle and promptly decided he must have made a mistake somewhere. He had some figures that didn't quite round out correctly. Light was clearly a wave. Scientists at the time agreed with him, and then Einstein came along and said, actually, I think you might be on the right track here. And a bunch of other scientists looked into it, and yes, Max Planck's paper was correct. He just didn't think it was because the answer didn't make sense. Louis de Broglie took this even further and discovered that not only is light a particle as well as a wave, but all particles are in fact also waves. Now you might argue, oh, I'm not a particle, I'd be a collection of particles. Well, as you will discover, even things like protons are actually also a collection of smaller particles, so that argument just doesn't work. You are, in a manner of speaking, a single particle that is a wave. Now, I mentioned that protons are a combination of smaller particles. They are made up of 3 quarks, 2 up quarks and a down quark. Up and down are 2 of the 6 flavours, which have nothing to do with how they taste. Also, don't confuse a quark's flavour with its colour, which has nothing to do with how it looks. What you're looking at here is the known elementary particles, adding in new words to your vocabulary like lepton and muon neutrino. What I will say is it's good you're studying physics now because the current curriculum doesn't include gravitons, which are far too hypothetical to teach about in school, but it does include a number of other force-carrying particles, being the gluon, the photon, and the W and Z bosons. You'll also be hearing a lot this year about where physics just doesn't know. Scientists are currently attempting to find the theory of everything which will unite all 4 fundamental forces. Thus far, gravity does not play well with the other 3. Similar to how scientists proved that light was a wave, and then later realised, oh, it's also particles, scientists at the moment have proved that gravity works. It fits the equations, our theories are true, it works. we've got the same thing happening for the other three fundamental forces. We have those working together: the strong nuclear force, the weak nuclear force, and electromagnetism. We have the three of them following our theories. The calculations hold true. We know what's going on with them. When we try to combine these, does not work. All breaks down at that point. There are some potential explanations, such as string theory, but they're still nowhere near detailed enough to be accepted by all scientists, let alone taught in schools. But don't worry, even though some Year 12 physics is, yeah, we have no idea, there's enough of it that is learning to keep you busy. And of course, there's yet another thing to do with trains. Did you know that a train travelling at near light speed can fit completely inside a tunnel that it is way too long for, while simultaneously being even more too long to fit inside that very same tunnel? These concepts seem strange, but there are calculations, there are equations, there are formula, and you will learn how to understand these and they will make sense to you. I trust you found this video helpful. Feel free to go back and have a look at any of the concepts that I've mentioned. Do some of your own research on them if you haven't come across them in class yet and want to have a better understanding by the time you get to them. Also, if you want help with how to revise for exams, well, John's done some videos on that, and you can contact AIM Academics to arrange a free 20-minute consultation about your study habits. No obligation, you can just get some extra help for nothing. Thanks for watching this video, and remember, don't forget units. Now obviously I only had a certain amount of time in this video, which I used to cover some concepts that will be important, but if you'd like to learn more about this, then AIM Academics does offer holiday revision courses for most of the subjects that you could be doing. Our July exam revision workshops are held during the second week of the holidays, and the more days you attend, the more we can teach you.